Hi dear students, it's me Vijay. Today we are going to discuss some MCQ question from chapter Structure of Atom. So I'll start with the first question. How many electron can fit in the orbital for n is equal to 3, L is equal to 1? Now here principal quantum number n is equal to 3 and azimuthal quantum number L is equal to 1. Now L1 means it indicate P subshell, right? P subshell. So L is equal to 1 indicate P subshell. L is equal to 0, S subshell, L is equal to 1, P subshell, L is equal to 2, D subshell, L is equal to 3, F subshell, right? F subshell. L is equal to 3, F subshell. 0 S, 1 P, 2 D, and L is equal to 3, F subshell. So here, N value is equal to 3, L value is equal to 1. L1 means P subshell. So the subshell is 3P. 3P subshell. So subshell is 3P, right? Now 3P. Now if you consider 3P, 3P subshell contain 3 orbitals, Px, Py, and Pz, right? Each orbital can accommodate 2 electrons. So number of electrons in 3P subshell. Number of electrons in 3P subshell is 6 electrons. Total electrons in 3P subshell is 3P subshell is 6 electrons. Now, how many electron can fit in the orbital? In the orbital, for 3p, there are 3 orbitals, px, py, pz. Each orbital contains 2 electron. So maximum, we can place maximum of 2 electron in each orbital. So how many electron can fit in the orbital? Not in the subshell. For in 3p subshell, total 3p subshell, we can place 6 electron. 3p subshell consists of 3 orbitals, px, py, pz. Each orbital can place maximum of 2 electron. So number of electrons in 3p orbital. One orbital of 3p subshell is 2 electron. How many electron can fit in the orbital? So each orbital is having 2 electron. Orbital for n is equal to 3, L is equal to 1. 2 electron. I think it's clear. I think it's clear. Moving on to, so you have to remember this 3p. This is 3p subshell. In 3p subshell, we can place maximum of 6 electron. That means each orbital, px can accommodate 2 electron, py can accommodate 2 electron, pz. These are orbital, px, py, pz orbital. Okay, these three combine to form 3p subshell. These three combines to form 3p subshell. Total we can place 6 electrons. So each orbital in each orbital we can place 2 electron. I think it's clear. Moving on to next question. Question number 2. Which of the following pair of d orbital will have electron density along the axis? Now we know that d orbitals, there are 5 d orbitals. There are 5 d orbitals. First one, let it be x and let it be y. First one, dxy. Now in dxy, electrons are present along in between the axis. Electrons are present between the axis. Okay, here, okay, these are electrons are present between the axis. Now second one, dyz, let it be y and this be z. So for dz, electrons are present between the axis. Electrons are present, it is not present in the axis, between the axis, dyz. Now for dxz, electrons are present between the axis, right? They are not in the axis, they are in between the axis. They are in between the axis, dxz. Now fourth one, dx square minus y square. Now in dx square minus y square, this is y. So in dx square minus y square, electrons are present along the axis. Electrons are present along the axis. Okay, electrons are present along the axis, dx square minus y square, and last orbital, that is dz square. Now for dz square, electrons are present along the axis. They are present along the axis. Along the axis, right? This is dz. dz orbital, and here electrons are present along the axis. So for d orbital, possess double dumbbell shape. D orbital possess double. They have double dumbbell. They have double dumbbell shape. they have double dumbbell shape. Okay, except dz square, rest of them have double dumbbell shape, right? Now, in dx square minus y square and dz square, electrons are, these are electrons are present. Electron density is along the axis. So, which of the following pair of d orbital will have electron density along the axis? So, along the axis, electron density is observed in the case of dx square minus y square and dz square. dz square and dx square minus y square. So, I think it's clear. So, second question, answer option 3. Moving on to next question, question number 3. Two electrons occupying the same orbitals are distinguished by two electrons occupying the same orbital. Consider 1s orbital. Now there are two electrons. Both of them have same principal quantum number, 1. Right? This is principal quantum number 1. And azimuthal quantum number 4s, azimuthal quantum number is equal to 0. So both of them have L value, okay. For s orbital, L value is equal to 0. S subshell, L value is equal to 0. So L value is equal to 0. Now ML value is calculated using this equation. Minus ML value is equal to minus L2. ML value is equal to minus L2 plus L. So here L value is equal to 0. So ML value is also equal to 0. Now both of them have same quantum numbers. Both of them have same values for 3 quantum numbers, but for last one, that is spin quantum number, S value is different for both the electron. This electron is focusing, or this electron is projecting, or this electron is spinning in clockwise direction, and this electron is spinning in anti-clockwise direction. So for S spin quantum number for this electron is plus half. Electron spinning in clockwise direction have plus half spin quantum number, and electron spinning in anti-clockwise direction have minus half spin quantum number. So two electron occupying the same orbitals are distinguished by spin quantum number. Spin, because for two electron in the same orbital, they have same principle, same azimuthal, same magnetic quantum number, only spin quantum number differs. So two electrons occupying same orbitals are distinguished by spin quantum number. Now, moving on to fourth question. The angular momentum of an electron in d orbital is equal to. Now, already we have studied it. Already we learned to calculate equation to calculate angular momentum. Orbital angular momentum. ORBITAL. Orbital angular momentum. Angular momentum of an electron in d orbital. So we have to calculate orbital angular momentum. What is the equation to calculate orbital angular momentum? Root of L into L plus 1 into h by 2 pi. This is the equation to calculate orbital angular momentum. Okay, so equation to calculate orbital angular momentum is equal to root of L into L plus 1 into h by 2 pi. So here electron is present in d orbital. Now electron is present in d orbital. For d orbital, L value is equal to 2, right? P, L value is equal to 1. Yes, L value is equal to 0. For F, L value is equal to 3. So here L value is equal to 2 because d orbital. So L into L plus 2, that is 2 into L into L plus 1, that is 2 into 2 plus 1 into h by 2 pi. That is 2 plus 1, 3. 3 2s are 6. Root 6 h by 2 pi. This is the value of orbital angular momentum. Now, here values are 0 h cross, root 6 h cross, root 2 h cross, 2 root 3 h cross. Now, this h by 2 pi is equal to h cross. This h by 2 pi is known as h cross. This h by 2 pi is known as h cross. Okay, this h by 2 pi. H is a constant value. H is having a constant value. H is a constant. Planck's constant. 2 pi is also a constant. So when you divide a constant with another constant, you will get another constant. That constant is h cross. So h by 2 pi is known as h cross. So instead of h by 2 pi, you can put root 6 h cross. Root 6 h cross. So answer option 2. H by 2 pi. H by 2 pi is equal to h cross. You have to learn this. H by 2 pi is equal to h cross. So instead of h by 2 pi, we can write h cross. So answer is root 2 h cross. I think it's clear. Moving on to next one. Question number 5. What is the maximum number of orbitals that can be identified with the following quantum number? N is equal to 3, L is equal to 1, ML is equal to 0. Now here, N is given as 3 and L is equal to 1, right? Now if L value is equal to 1, ML value can be, what is the equation to calculate ML value? ML value is equal to minus L to plus L. So here L value is equal to 1. So ML value is equal to minus 1, 0, plus 1, right? If L is equal to 1, ML can have value. ML is calculated using this equation. ML is calculated using this equation. ML is equal to minus L to plus L. That is ML is equal to minus 1, 0, plus 1. Now L1 means it is p orbital. So p subshell contain 3 orbitals. P subshell contain 3 orbital px, okay, py, pz. So let px be minus 1, py be 0, and pz be 1. Okay, here n value is equal to 0 and L value is equal to 1. L value means p orbital. L value 1 means p orbital. Now ML value is calculated using this equation minus L to plus L. So if L value is equal to 1, ML value is equal to minus 1 to plus 1, that is minus 1, 0, plus 1. So these are 3 p orbitals. Minus 1 for px, 0 for py, and 1 for pz. Minus 1, 0, plus 1, right? Now, what is the maximum number of orbitals that can be identified with the following quantum number? N is equal to 3, L is equal to 1, ML is equal to 0. Now, N3, L1, that is 3p, right? 3p. Now 3p possesses 3 orbital, and here ML is equal to 0. ML is equal to 0 means this orbital. So here 3p, and this is 0. ML value is 0. How many orbitals are there like that? How many orbitals are having value like that? N is equal to 3, L is equal to 1, ML is equal to 0. Only one orbital, right? This orbital is having value. N is equal to 3, right? L is equal to 1. P orbital means 1. And ML value is 0. That is for only one orbital. These values are possible only for one orbital. So answer is option 1. I think it's clear. Okay, here N is given as 3, L is given as 1, that is p orbital. Now ML value is minus L to plus L, that is minus 1, 0, plus 1. Okay, so we can easily identify the subshell. Here subshell is 3p, right? Now 3p subshell, this is 3p subshell. Now 3p subshell possesses 3 orbital px, py, pz. Now px be minus 1, py be 0, and pz be plus 1. These are the values. So how many orbitals can be identified with the following? N3, L1, ML is equal to 0. So ML value 0 means we can identify only one orbital, right? This orbital is having N3, N value 3, L value, that is p orbital 1, and ML value 0. So there is only one orbital. So answer option 1, right? Answer option 1. I think it's clear. Moving on to next question. Calculate the energy in joules corresponding to the light of wavelength 45 nanometer and Planck's constant 6.63 into 10 raised to minus 34 joules second. Speed of light is equal to 3 into 10 raised to 8 meter per second. We calculate the energy in joules. So we have to calculate energy in joules. Now we know that E is equal to h nu, right? Now what is nu? What is the relation between nu and lambda? Nu and wavelength. Nu means frequency. Okay. Now here wavelength is given. Here wavelength is lambda is equal to, here wavelength is given. Here wavelength lambda is given 45 nanometer. H value is already given and velocity of light is given 3 into 10 raised to 8 meter per second. Now first you have to convert nanometer to meter because here velocity of light is given in meter. So you have to convert nanometer to meter. That is 45 into 10 raised to 9 meter. 1 nanometer. Nanometer means 10 raised to minus 9 meter. So here wavelength of light is given, velocity of light is given, and h values, we know the value of h. Okay, we have to calculate energy, right? Now, we have to calculate energy. We know that E is equal to h nu. According to Planck's quantum theory, E is equal to h nu. Now, what is the relation between nu and wavelength? Nu is equal to c by lambda, right? Nu is equal to c by lambda. Now, substituting value of nu here, that is E is equal to h c by lambda. E is equal to h c by lambda. So, E is equal to, what is the value of h? 6.63 into 10 raised to minus 34 into velocity of light 3 into 10 raised to 8 meter per second divided by now wavelength lambda, which is equal to 45 into 10 raised to minus 9 meters. Now, after multiplying these two values and divide by 45, you will get 0.442 into 10 raised to minus 17. Okay, you will get 10 raised to 0.442 into 10 raised to minus 17. Or you can write 4.4. I'm taking this point to this side. 4.42 into 10 raised to minus 18. 4.42 into 10 raised to minus 18. Answer option D. Okay, here we have to calculate energy. We have to calculate energy in joules, and wavelength of light is given in nanometer, which is equal to 45 nanometer. Okay, and velocity of light is 3 into 10 raised to 8 meter per second. Now here velocity of light is given in meter, so you have to convert nanometer to meter. Nanometer is equal to 10 raised to 9 meter, right? Now we know the equation according to Planck's quantum theory. P-L-A-N-C-K-S, Planck's quantum theory. According to Planck's quantum theory, E is equal to h nu. But we don't know the value of nu, right? We don't know the value of nu. So we know the value of wavelength, right? We know the value of wavelength, but we don't know the value of frequency. So we can calculate frequency by using the equation nu is equal to c by lambda. Or you can substitute this value directly here. Instead of nu, you can write c by lambda. That is 6.63 into 10 raised to minus 34. H value is given into velocity of light 3 into 10 raised to 8 divided by 45 into 10 raised to minus 9 meter. After cancelling, you will get 0.442 into 10 raised to minus 17. I'm taking 1 point to the side. So you'll get 4.42 into 10 raised to minus 8. Answer option D. I think it's clear. Moving on to next question. Question number 7. Be2 plus is isoelectronic with which of the following ion? Now, Be, beryllium, atomic number 4, configuration 1s2, 2s2, right? Now, Be2 plus means we have to remove 2 electrons from beryllium. So you will get 1s2, right? These 2 electrons are removed, so 1s2. Now, for which species? Isoelectronic means same number of electrons. So Be2 plus is isoelectronic with which of the following species? Same electron. Same electron. Now Be2 plus contain or it possesses 2 electron. So we have to find the species which contain 2 electron. Answer option 2, lithium, because lithium atomic number 3, configuration 1s2, 2s1. Now lithium plus means we have to remove 1 electron. So you will get 1s2. 1 electron is removed from 2s. So Li plus means 2 electron. Li plus means 2 electron. So Be2 plus 2 electron. Li plus means 2 electron. So both of them have same number of electrons. Same number of electrons. That means they are isoelectronic. Iso same. Iso means same number of electron. Isoelectronic. I think it's clear. Moving on to next question. Question number 8. Which is the maximum number of electron that can be associated with the following set of quantum number? N value is equal to 3. L value is equal to 1. So orbit subshell is 1 means it is P, right? So subshell is 3P. Now 3P possesses three orbitals, 3p possesses three orbitals, px, py, pz. Now, ml value is equal to, if L value is equal to 1, ml value is equal to minus L2 plus L, that is minus 1, 0, plus 1. So these are the orbital minus 1, 0, plus 1. Now, what is the maximum number of electron that is associated with the following quantum number? N3, L1, m is equal to minus 1. That is this orbital. 3p, 3p, N3, L1, and ml value plus 1. ml value minus 1. Sorry. Not this orbital, this orbital. ml value minus 1. So ml value minus 1. Right? 3p. N value 3, p. L is equal to 1 and ml minus 1. This orbital. Now, maximum number of electron placed in this orbital, 2 electron. According to Pauli's exclusion principle, an orbital can accommodate maximum of 2 electron. So, number of electron present in this orbital, that is minus 1. N is equal to 3, L is equal to 1, minus L is equal, ml is equal to minus 1 as 2 electrons. So, we can place maximum of 2 electrons. I think it's clear. Moving on to next question, question number 9. The value of Planck's constant is 6.63 into 10 raised to minus 34 joules second. The speed of light is 3 into 10 raised to 17 nanometer per second. Which value is closest to the wavelength in nanometer of a quantum of light with frequency 6 into 10 raised to 15 second inverse? Okay, now here h value is given. H is equal to 6.63 into 10 raised to minus 34 joules second. Velocity of light is given in nanometer, that is 3 into 10 raised to 7 nanometer per second. And frequency of light is given 6 into 10 raised to 15 second inverse, right? Now, value of Planck's constant 6.63. Okay. Now we have to calculate wavelength in nanometer. Right? So wavelength, lambda is equal to, what is the equation relating lambda, nu and velocity of light? Lambda is equal to c by nu. So lambda is equal to 3 into 10 raised to 7 nanometer per second. Now, no need to convert this nanometer to meter because we have to calculate wavelength in nanometer. So, no need to convert this nanometer to meter. Divide by frequency. 3 into 10 raised to 17. Sorry, it is 3 into 10 raised to 17. 3 into 10 raised to 17. 3 into 10 raised to 17 nanometer per second. And frequency 6 into 10 raised to 15 second inverse. Second inverse cancel each other. Now, if you divide this value with this value, you will get wavelength across. So it is 1 by 2, and this is 1 by 2 into, I'm taking 10 raised to 15 to this side. So it will become 10 raised to 17 into 10 raised to minus 15, which is equal to half into 10 raised to 2, which is equal to 0.5 into 10 raised to 2, which is equal to 1 to 50 nanometer. You will get 50 nanometer. Answer option 2. You will get 50 nanometer. Answer option 2, 50 nanometer. I think it's clear. Moving on to next question. Question number 10. Based on the equation E is equal to minus 2.178 into 10 raised to minus 18 joules Z square by N square, certain conclusions are written. Which of them is not correct? Larger the value of N, larger is the orbital radius. Larger the value of N, that means if we consider one orbit, let this be N is equal to 1. Let this be N is equal to 1. N is equal to 2. Okay. N is equal to 3. N is equal to 4. So, larger the value of N, larger the value on, greater will be the orbital size, right? As N value increases, radius also increases. For N is equal to 1, radius is R1. Now, for N is equal to 2, radius is R2. R2 is greater than R1. Now, for N is equal to 3, radius is R3. Now for n is equal to 4, radius is r4. So as n value increases, radius increases. So this one is right. Which of the them is not correct? This one is correct. Okay. Now second one. Equation can be used to calculate the change in energy when the electron changes orbital. Right. Now if you know the value, let the energy of first orbital be E1, let the energy of second orbital be E2, third orbital E3, fourth orbital E4. Now if we know the energy value of each orbit, and if electron is jumping from this orbital to this orbital, if electron is jumping from this orbital to this orbital, if electron is jumping from this orbital to this orbital, you can easily calculate the energy difference if you know the energy of each orbital. Delta E is equal to E2 minus E1, right? If an electron jumps from E1 to E2, okay, you can calculate, equation can be used to calculate energy change in energy when the electron jumps, right? When an electron jumps from first orbit to second orbit, or when it jumps from second orbit to first orbit, when an electron jumps from second orbital to first orbital, you can easily calculate the energy change by using this equation. Delta E is equal to E2 minus E1, right? So this is also correct. We can easily calculate the energy change if we know the energy of the orbits. I think it's clear. Now third one, for n is equal to 1, the electron has more negative energy than it does for n is equal to 6, which means that that electron is more loosely bound in the smallest allowed orbital. For n is equal to 1, the electron has more negative energy than it does for n is equal to 6, which means that the electron is more loosely bound in the smallest orbital. Now my question is, here this electron, when an electron is present in n is equal to 1, when an electron is present in n is equal to 1, when an electron is present in n is equal to 1, okay, I'm rubbing this one, these values. Now, when an electron is present in n is equal to 1, it is near to nucleus, so this is strongly attracted. Now, when an electron is present in n is equal to 2, now it is little bit away from the nucleus, so attraction decreases. Now, when an electron is present in n is equal to 3, now again it is somewhat like, I mean, it is little bit farther from the nucleus, so attraction decreases. Now, if an electron is present in n is equal to 4, again that electron is placed away from the nucleus, so attraction decreases. So, electron present in n is equal to 1 are attracted. Electrons present in n is equal to 1 are attracted strongly than when electron is present in n is equal to 4. So electrons present in n is equal to 1 are attracted strongly because they are near to nucleus. Now, an electron present in n is equal to 4, they are attracted weakly because they are the distance between nucleus and the last electron, that is fourth electron, n is equal to fourth electron, distance is very large, so attraction decreases. Here they see that, which means that electron is more loosely bound in the smallest allowed orbital. That means here attraction is less. For n is equal to 1, attraction is less. That is not correct. Electrons near the nucleus are attracted strongly than electron farther away from the nucleus, So in n is equal to 1, electrons are strongly attracted than electrons present in n is equal to 4, right? It's a logic. So which means that, so this is wrong because the electron is more loosely bound in the smallest orbital. In smallest orbital, they are not loosely bound. They are strongly attracted. Loosely bound means attraction is less. In n is equal to 1, lowest orbit, they are strongly attracted. They are not loosely bounded. But as the distance from the nucleus increases, electrons are loosely bound. Their attraction decreases. So this one is wrong. So answer is option 3. Anyway, we can check fourth one also. The negative sign in the equation simply means that the energy of the electron bound to the nucleus is lower than it would be if the electrons were at infinite distance from the nucleus. Yeah, the negative sign in the equation simply means that the energy of the electron bounded to the nucleus is lower than it would be if the electrons were at infinite distance. Yeah. Electron present at the nucleus, near to the nucleus, they have stronger attraction. That means they are stable. They are strongly attracted. That means these electrons are stable. So electrons near to the nucleus are strongly attracted, so they are stable. For stable electrons, energy is less because stability and energy are inversely proportional. Stability and stability and energy are inversely proportional. Stability and energy are inversely proportional. So electron near the nucleus are strongly attracted. That means their energy is less, so their stability is more. And a negative sign simply in equation simply means that the energy of electron bound to the nucleus is lower than it would be if the electrons were at infinite distance from the nucleus, right? So electron present near the nucleus, electron bound to the nucleus near to the nucleus is lower because they are strongly attracted, so their energy is less. Okay, their stability is more. So this one is also correct. So wrong one is third. I think it's clear. I think it's clear. Electron near to the nucleus are strongly attracted. That means their energy values are less. Their energy values are less and they are more stable compared to electron further away from the nucleus. Now, if electron further away from the nucleus, okay, they are not attracted strongly, so they have some little bit energy. Okay, I think it's clear. I think it's clear. Now, always remember that energy near to orbital energy near to the nucleus is always less than the, okay, if you consider energy of E1 and E4, energy of E1 is less because it is near to the nucleus, and energy of E4 is greater because it is further away from the nucleus. Okay, you should always remember that E1 is near to the nucleus, so energy is less. E4 is further away from the nucleus, so energy is greater than E1. E1 compared to E1, energy of E4 is greater than E1. Okay, I think it's clear. I think it's clear. So moving on to question number 11. The correct set of 4 quantum numbers for the valence electron of rubidium atom. Rubidium, RB. Now we have to calculate, we have to find the quantum numbers for last electron of rubidium atom. Now if you don't know the atomic number of rubidium atom, but you know, if you know the group in which electron, in which rubidium is present, you can easily find the orbital, last valence orbital of rubidium atom. We know that rubidium belongs to first group. For lithium, first group lithium, sodium, potassium, rubidium, cesium, and francium. Rubidium belongs to first group. And if you don't know the exact atomic number of rubidium, but if you know group number, you can find the valence electron. For lithium, atomic number 3, configuration 1s2, 2s1. Now sodium, atomic number 11, configuration 1s2, 2s2, 2p6, 3s1. Now potassium, atomic number, so configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, right? 2 plus 1, 3. 2 plus 2, 4 plus 6, 10 plus 1, 11. 2, 2, 4, 6, 10, 12, 2, 12 plus 8, 18, 19, right? 19. Now here in lithium, last electron is present at 2s orbital. In sodium, last electron is present in 3s orbital. And for potassium, last electron is present in 4th orbital, right? 2s1, 3s1, 4s1. For potassium, last electron is present in 4s orbital. So obviously, for rubidium, last electron is present in 5s orbital, 5s1. Now for cesium, last electron is present. Last electron is present at 6s1, present in a 6s1 orbital. Now for francium, it is 7s1. You can easily identify the orbital in which last electron is present. Okay, so here rubidium, last electron is present in 5s1 orbital. Now 5s1, 5s, right? 5s orbital, last electron is present in 5s orbital. I think it's clear. Now here n value is equal to 5. 5s, n value is equal to 5. And L value is equal to, for s orbital, L value is equal to 4s, L is equal to 0, right? For s orbital, L value is equal to 0. For s orbital, L value is equal to 0. P orbital, L is equal to 1. For D, L value is equal to 2. For F, L value is equal to 3. So here, for S orbital, L value is equal to 0. So L value is equal to 0. Now ML value is calculated using this equation. ML is equal to minus L to plus L. Here, L value is equal to 0. So ML value is equal to 0. So ML is equal to 0. Now S value is equal to plus or minus half. Let it be plus half or minus half. So answer for quantum number N5, L0, ML0, S is equal to half, plus half or minus half. It can be plus half or minus half. So answer is option 1. N value 5, L value 0, ML value 0, ML value 0, and S value plus half. So answer option 1. I think it's clear. Option 1. I think it's clear. Moving on to next question. Maximum number of electron. Question number 12. Maximum number of electron in a subshell. L is equal to 3 and N is equal to 4. So L value is equal to 3 and N value is equal to 4. So L value 0 S, L value 1 P, L value 2 D, and L value 3 means F orbital. So here subshell is F subshell. F subshell, right? L value 3 means it is F subshell. So N value 4 means 4F subshell. So we have to calculate maximum number of electron in 4F subshell. Now we know that for F there are 7 orbitals. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. For F subshell, there are 7 orbitals. Each orbital can place maximum of 2 electrons. So number of electrons in 7 orbital, 14 electrons. So maximum number of electron present in subshell with L is equal to 3, N is equal to 4. So N4L3 means it is 4F subshell. For F subshell, there are 7 orbital. Each orbital can place maximum of 2 electrons. So there are 14 electron. Answer option 3, 14 electrons. I think it's clear. Moving on to next question. 13th one. The orbital angular momentum of P electron is given by. Now, orbital angular momentum. What is the equation to calculate orbital angular momentum? Orbital angular momentum is equal to root of L into L plus 1 into H by 2 pi, right? Now for P orbital, L value is equal to 1. For P orbital, L value is equal to 1. So angular momentum, orbital angular momentum is equal to root of 1 into 1 plus L into L plus 1. That is 1 into 1 plus 1 into H by 2 pi. That is equal to root 2. 1 plus 1, 2. 2 into 1, root 2 H by 2 pi. Or you can write root 2 H by 2 can be written as root 2 into root 2 pi. We can write 2 into 2 like this, root 2 into root 2. So this root 2 and root 2 cancel each other. You will get angular momentum is equal to H by 2 root 2 pi. H by root 2 pi. H by root 2 pi. Answer option 1. H by root 2 and pi. Root 2. It is root of 2 pi. It is not root of 2 pi. It is root 2 into pi. Pi is outside the root. I think it's clear. Answer option 1. Next question number 14. The total number of atomic orbital in 4th energy level of an atom. 4th energy level. Total number of atomic orbital in 4th energy level. 4th energy level means N is equal to 4, right? Now N is equal to 4, L can have value. L is calculated using this equation 1, 0 to N minus 1. L is calculated using this equation 0 to N minus 1. So N value 4 means L can have value 0, 1, 2, 3. N value 4 means L can have value. L value is calculated using this equation. L is equal to 0 to N minus 1. So N value is equal to 4 minus 1 is equal to 3. 0 to 3. 0 to 3. That is 0, 1, 2, 3. Now, ML value for L is equal to 1 is equal to 0. Now, ML value for L is equal to 1 is minus 1, 0, plus 1. 3 orbitals. Here only one orbital, only one value, one orbital. Now ml value for L is equal to 1 is equal to minus 1, 0, plus 1, 3 orbital. Now ml value for L is equal to 2. ml value for L is equal to 2 is minus 2, minus 1, 0, plus 1, plus 2, right? So ml value for L is equal to 2 is minus 2, minus 1, 0, plus 1, plus 2, minus 2, minus 1, 0, plus 1, plus 2. 5 orbital. Okay, 5 orbitals. Now, for L is equal to 3, L is equal to 3, ml can have value minus 3, minus 2, minus 1, 0, 1, 2, 3. 7 orbitals. Minus 3, minus 2, minus 1, 0, 1, 2, 3. 7 orbital. Now, here n is equal to 4. L can have value. L is calculated using the equation 0 to n minus 1. Right. So, L is equal to 0 to n minus 1. N is 4. 4 minus 1, 3. That is 0, 1, 2, and 3. 0, 1, 2, and 3. L can have value 0, 1, 2, and 3. 1, 2, and 3. Now, if L value is equal to 0, then ML value is equal to 0 because ML is calculated using this equation minus L2 plus L. For 0, there is only one value. ML is equal to 0, only one orbital. Now, for L is equal to 1, ML can have value minus 0, minus 1, 2, plus 1. That is minus 1, 0, plus 1, 3 orbital. Now, if L is equal to 2, ML can have value minus 2, minus L2 plus L. That is minus 2, minus 1, 0, plus 1, plus 2, 5 orbitals. Now, if ML value is equal, L value is equal to 3, ML can have value minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3, 7 orbital. Now, total number of atomic orbital in fourth, and how many atomic orbital are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There are 16 orbital. Answer is option 3. 16 orbitals are there. I think it's clear. But the problem is it is a very complicated method, right? It's a very complicated method. So I'm going to tell you a easy method to calculate number of atomic orbital in a fixed energy level. This is a complicated method. This is a complicated method, but okay, you can use this method to calculate number of orbitals in a particular energy level, but it's a complicated method. So I'm going to tell you an easy method to calculate number of orbitals in a fixed energy level. Orbital in a particular energy level, in a particular energy level. So number of orbital in a particular energy level can be calculated using this equation n square. For example, number of orbitals in first level 1 square 1. Number of orbitals in second level, number of orbitals in first level n is equal to 1. Number of orbitals 1 square, that is 1 orbital. Now number of orbitals in second level 2 square, 4 orbitals are there. Number of orbitals in third level 3 square, 9 orbitals are there. Number of orbitals in fourth level 4 square, that is 16 orbital, right? 16 orbitals are there in fourth level. So you can easily calculate number of orbital in a particular level using this equation n square. N means the orbital in which the energy level. N means the energy level. So for fourth energy level, fourth orbit, number of orbit, not orbital, it's orbit, O-R-B-I-T, orbit. So number of orbits or number of orbital in a particular energy level or particular orbit is equal to n square. N is the energy level or orbit. So in the case of fourth energy level, that is fourth orbit, number of orbital is equal to 4 square, that is 16. I think it's clear. Moving on to next question, question number 50. Here, if n is equal to 6, the correct sequence of filling of electron will be ns, np, n minus 1d, n minus 2f, ns, n minus 2f, n minus 1d, np, ns, n minus 1d, n minus 2f, np, ns, n minus 2f, np, n minus 1d. So here, each option there are four subshells are given: ns, Np, n minus 1d, and n minus 2f, right? Now ns, here n value is equal to 6. So ns means 6s, 6s. Np means 6p. Now n minus 1d means 6 minus 1, that is 5, 5d. And n minus 2f means it is 4f. So here these are the four orbitals. Ns means 6s because n value is 6. So ns means 6s. Np means 6p. N minus 1d, that is 6 minus 1d, that is 5d. And n minus 2f, that is 4f. So we have to find the correct sequence of filling of electron. To find the correct sequence of filling of electron, N plus L rule will help us to find the correct sequence of filling of electron. Now, for 6s, N plus L value is equal to 6 plus, for S orbital, L value is equal to 0. So 6 plus 0, 6. Now, for 6p, 6 and L value is equal to 1. N is 6, N is 6 and L value is equal to 1, 7. Now, for 5d, N value is equal to 5 and the D value is equal to 2, that is 7. Now for 4f, N value is equal to 4 and L value is equal to 3, that is 7. So this is having lowest N plus L value. So first we have to fill ENS orbital, that is 6s orbital. First we have to fill ENS orbital, that is 6s orbital. So this is having lowest energy value. Okay, so we have to first fill ENS, that is 6s orbital. Now all these three have same N plus L value. So if all of them have same N plus value, the lowest energy, the lowest N value will have lower energy and highest N will have highest energy. The orbital having, if N plus L value for three orbitals are same, then you have to find N value. Here, 4f is having lowest N value. That means it is having lowest energy. Okay, compared to 4f, 5d is having higher N value. So compared to 4f, 5d is having higher energy. Now compared to 5d, 6p is having higher N value. So compared to 5d, 6p is having higher energy. So if more than one orbital have same N plus L value, if more than one orbital have same N plus L value, okay, you have to check N value. Orbital having lower N value will have lower energy, and orbital having higher N value will have higher energy. So here first we have to fill 6s, then 4f, then we have to fill 4f because these three have same energy. These three have same energy. So you have to check N value. N value is lowest for 4f. So 4s will have lower energy. So 4f means N minus 2f. Then lower energy is for 5d. So you have to fill N minus 1d. That is 5d. Then last N value is greater for 6p. So then you have to fill NP. That is 6p. So NS, after NS, N minus 2f, then N minus 1d, then NP. NS, N minus 2f, then N minus 1d, NP. So to find the sequence of filling of electron, find the energy level of each orbital using N plus L rule. Find the energy of each orbital using N plus L rule. If more than one orbital possesses same energy, same N plus L value, then orbital having higher N value will have higher energy and orbital having lower N value will have lower energy. I think it's clear. So answer is option 2. Moving on to next question, question number 16. According to Bohr theory, which of the following transition in hydrogen atom will give rise to least energetic photon? Okay, 6 to 5, 5 to 3, 6 to 1, 5 to 4. So here these are the orbital. Let this be the nucleus. I'm not drawing circular orbital. Let this be the N is equal to 1. Let this be N is equal to 2. Let this be N is equal to 3. And let this be N is equal to 4. Let this be N is equal to 5. And let this be N is equal to 6. Okay, so these are the orbital. I'll draw once more. Okay, I'm not drawing circular orbits. I'm not going to draw circular orbits. Okay, actually orbits are circular, but I'm not going to draw circular orbits. Okay, let this be the nucleus. This is N is equal to 1. Okay, this is n is equal to 2. This is n is equal to 3. This is n is equal to 4. This is n is equal to 5. N is equal to 6. Okay. Now you should remember one thing. As distance from the nucleus increases, orbital will come closer each other. Here, the distance between orbital is very large, but here distance between the orbitals decreases. Here again it is decreases, again decreases. Here again decreases. Here again decreases. So, as the orbit move from the nucleus, the distance between the orbital is getting reduced. Okay, here the distance between these two orbital is greater. Here they are nearby. Here they are again nearby. Here they are again nearby. Here they are again nearby. Right. So here an electron is moving. First option, electron is jumping from. Okay, I'll start with third option. Here an electron is jumping from sixth level to. An electron is jumping from sixth level to first level. Energy difference is greater. Here, energy difference is greater because electron is jumping from sixth level to first level. Energy difference is greater, right? Which of the following transition in hydrogen atom will give rise to least energetic photon? Here, energy difference is greater, so it will produce higher energy radiation. Okay, so answer is not option 3 because here when an electron jump from 6 to 1, okay, the energy difference is greater, so the amount of light, the light liberated will have higher energy. The light liberated has higher energetic radiation. Now 5 to 3. This is 5 and 5 to electron is jumping from 5 to 3. Compared to this one, so compared to this transition, energy is less for this transition. Okay, now next one, 5 to 4. This is 5 to 4. Now compared to this transition, energy is lesser for this transition. Energy liberated will be lesser because the energy difference between the two orbitals is very less. So energy liberated will be less. Now compared to this 6 to 5, this again lesser, right? Again lesser. The energy difference between these two orbits are less. That means when the electron jump from 6 to 5, the radiation emitted will be lower energy radiation. That is, they will produce least energetic photon. So answer is option 1. I'll explain once more. If you consider option 3, electron is jumping from 6 to first orbital. Energy difference between these two orbits is larger, so they will produce high energy radiation. Now, so this is not the answer. N is equal 5 to 3. 5 to 3 means here this electron is jumping from here to here. Energy will be liberated. Compared to 6 to 1, energy is less because energy difference between these two orbitals is energy difference between two orbit is less, so energy liberated will be less compared to this. Now 5 to 4 means electron is jumping from here to here. Compared to 5 to 3, 5 to 4, energy difference between 5 to 4 is again less, so liberated energy radiation will have lower energy. Now next last one is 6 to 5. 6 to 5 means here the energy between these two orbitals is least, so when this electron jump from 6 to 5, the radiation emitted will have least energy. So answer is 6 to 5. I think it's clear. Moving on to next question number 17. A 0.66 kilogram ball is moving with a speed of 100 meter per second. The associated wavelength will be. So here mass of a ball is given 0.66 kilogram. Velocity is given 100 meter per second. We have to calculate wavelength. Now relationship between m lambda v is lambda is equal to h by mv. De Broglie wavelength equation. Lambda is equal to h by mv. This is the relationship between lambda, wavelength, mass and velocity. Lambda is equal to h by mv. H is equal to 6.626 into 10 raised to minus 34 divided by mass 0.66 into velocity 100. Here velocity is expressed in SI unit, mass is expressed in SI unit. So no need to convert kilograms to grams. Okay, both are in SI unit. So 0.66 into 100. So you will get, after division, after dividing these two numbers, you will get 1 into 10 raised to minus 35 meters. 1 into 10 raised to minus 35 meters. So answer option 3. 1 into 10 raised to minus 35 meters. Now after dividing these two, you will get 1 into 10 raised to minus 35 meters. Okay, I think it's clear. This is de Broglie equation. This equation is known as de Broglie, Broglie equation. So moving on to next question, question number 18. The energy absorbed by each molecule A2 of a substance is 4.4 into 10 raised to minus 19 joules, and bond energy per molecule is 4 into 10 raised to minus 19 joules. The kinetic energy of the molecule per atom will be. So here AA molecule is there. The energy absorbed by each A2 molecule of a substance. Now AA molecule is there. AA molecule is absorbing 4.4 into 10 raised to minus 19 joules energy. A2 molecule, that is AA molecule. A2, this is A2. A2 molecule is absorbing 4.4 into 10 raised to minus 19 joules energy. And their bond energy per molecule is 4 into 10 raised to minus 19 joules. That is energy required to break this bond. Energy required to break, that is the bond energy. Bond energy of AA, that is energy required to break the bond between AA, is 4.0 into 10 raised to minus 19 joules. Okay, 4.0 into 10 raised to minus 19 joules. Now, what is the kinetic energy of the molecule? Now, listen carefully. Okay, we are supplying 4.4 into 10 raised to minus 19 joules, and energy required to break AA is 4 into. Okay, so from the energy given 4.4 into 10 raised to minus 19 joules of energy given, it used 4.0 into 10 raised to minus 19 energy to break this bond. So from this much of amount of this much energy is absorbed to break this bond. Okay, so we are supplying, please listen carefully, we are supplying, this is AA. Okay, to break AA, we need 4.0 into 10 raised to minus 19 joule. The bond energy per molecule is 4.0 into 10 raised to minus 19 joules. We are supplying 4.4 into 10 raised to minus 19 joules. So from this amount of energy, from the energy supplied, a molecule undergo cleavage by absorbing this much of energy. So remaining energy, what is the remaining energy? The remaining energy, that is 4.4 into 10 raised to minus 19 minus 4.0 into 10 raised to minus 19, which is equal to 0.4. 0.4 into 10 raised to minus 19 joules. This much of energy remaining, right? We are supplying 4.4 into 10 raised to minus 19 joules. From that, 4.0 into 10 raised to minus 19 joules is absorbed to break, to undergo cleavage. So remaining energy is 0.4 into 10 raised to minus 19 joules. Okay. Now they will equally distribute this energy. They will equally distribute, or they will equally absorb this energy, that is 4.4 into 10 raised to minus 19 by 2, that is 0.2 into 10 raised to minus 19 joules. They will equally absorb 0.2 into 10 raised to minus 19 joules, 0.2 into 10 raised to minus 19 joules, and this energy, by using this energy, they will move from here. That is the kinetic energy. That is the kinetic energy. So kinetic energy of the molecule per atom will be 0.2 into 10 raised to minus 19 joules, or you can write it as 2 into 10 raised to minus 20 joules. 2 into 10 raised to minus 20 joules. Answer option 4. I'll explain once more. Finally, I will explain last time. Please listen carefully. Here we are supplying. Here we have a molecule, and molecule is A2. A2 is having a bond. Let the bond be. Let this be the bond. And the energy required to break this bond is 4.0 into 10 raised to minus 19. After cleavage, they will exist as A atoms. A atom, A atom, right? Now, energy required to cleave this bond is this much. We are supplying 4.4 into 10 raised to minus 19 joules. We are supplying this much joules, and it absorbs 4.0 into 10 raised to minus 19 joules. Okay. So, after absorbing, remaining energy is from this much amount of energy is used to break this bond. Now, the remaining amount of energy is zero point 0.4 into 10 raised to minus 19. Okay, these energy will absorb equally by these two atoms, and they will escape. After absorbing that energy is their kinetic energy. Okay, they will absorb and they will move. By using that energy, they will move. That is their kinetic energy. So 4.4 into 10 raised to minus 19 is equally distributed between these two atoms. So 0.2 into 10 raised to minus 19, or you can write 2 into, I'm taking this point here, 2 into 10 raised to minus 20. Answer option 4. I think it's clear. I think it's clear. It is similar to photoelectric effect. It is similar to photoelectric effect. I think it's clear. Moving on to question number 19. Which one of the following element with the following outer orbital configuration may exhibit the largest number of oxidation state? Okay. Now, if you consider this, it can show oxidation state such as +2 or +1 by losing this electron +1, by losing one more electron from 3D +2, one more electron from 3D +3, +4, +5, +6. So it contains 4s1 and 3d5, right? So it can lose one electron from 4s. So +1 oxidation state. One electron from 4s and one electron from 3D, 2 +2. One electron from 4s and 2 electron from 3D. So you'll get +3. One electron from 4s and 3 electron from 3D. 1, 2, 3 and 1. +4. One electron from 4s and 4 electron from 3D. So it will show +5. And one electron from 4s and 5 electron from 3D. You get +6. Now one more thing. +1 oxidation state is not stable. So this configuration can show +2, +3, +4, +5, +6. This configuration can show these oxidation state. Now second one. Okay. Now this one can lose 2 electron from 4s. So we'll get +2. 2 from 4, 1 from 3D, +3. 2 from 4s, 2 from 3D, +4. 2 from 4s and 3 from 3D, 2, 3, 4, 5, +5. 2 from 4s and 4 from 3D, +6. And 2 from 4s, 5 from 3D, +7. So this can show +2, +3, +4, +5, +6, +7. And this one, this can lose, okay. 2 from 4s, so +2. Okay. 2 from 4s, 1 from 3D, you will get +3. 2 from 4s, 2 from 3D, +4. So it can show 3 oxidation state. Now this one, 4s to 3D3. It can lose 2 electron from 4s, +2. 2 from 4s, 1 from 3D, +3. 2 from 4s, 2 from 3D, +4. 2 from 4s and 3 from 3D, and +5. So which one of the element which one of the element with the following outer electronic makes with larger number of oxidation state? It is this one. It can show +2, +3, +4, +5, +6, +7. Now this molecule, we may think that it can show +1, but that is not possible. +1 configuration is not possible. Okay, it is not stable. It is stable only for copper. Copper will show +1, but for other D block elements, +1 is not stable. These are D block elements. For other D block element, +1 state is not stable. +1 is stable only for copper. For other, +1 is not stable. So this one, this is actually chromium. Chromium will not show +4 oxidation state. So it can show 1, 2, 3, 4, 5. 5 oxidation state. It can show 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Plus 6 oxidation state. 3 oxidation state, 4. So maximum is observed in the case of the this one. This is manganese. This one chromium. This is the configuration, outer configuration of chromium. This one is outer configuration for manganese, and this is for titanium, and this one is for vanadium. Okay, maximum is observed in the case of manganese. Now, question number 20. Maximum number of electron in a subshell of an atom is determined by following. Maximum number of electron in a subshell of an atom is determined by the following. So we have to find the equation to calculate maximum number of electron in a subshell. Now it is very easy. We know that 1s subshell contain 2 electron. 2s also contain, maximum it contain 2 electron. 2p contain maximum of 6 electron, right? Now substituting the value of L for s orbital, L value is equal to 0. So if you substitute here 2 into 0 plus 1, you will get 1, but maximum is 2. Number of electrons is 2. So this is not the answer. L minus 2. Now for us L value is equal to 2, so you will get 4 into 0. L value is equal to 0. For us L value is equal to 0, so substitute the value. 4 into 0 minus 2, which is equal to minus 2. Number of electron minus 2. That is not possible, so this is not the answer. 2n square. It is not the right answer. You know that subshell means you cannot use this equation. And last one, 4l plus 1. Now for 1 as L value is equal to 0, so 4 into 0 plus 2, you'll get 2 electron, right? 2 electron. Now for 2s, S value is L value is equal to 0, so 4 into 0 plus 2, again 2 electron. That's right. Now for 2p, for p L value is equal to 1, so you'll get 4 into 1 plus 2. 4 into 1 plus 2, you'll get 6 electron. So right equation is 4l plus 2. So if you know the azimuthal quantum number, you can calculate the number of electron using this equation. If you know the azimuthal quantum number, you can easily calculate the number of electrons in that subshell by using this equation. For example, for d orbital, L value is equal to 2. So number of orbital 4 into 2. Number of electrons 4 into 2 plus 2. 4 into 2, 8 plus 2, 10 electron. We know that d orbital can accommodate maximum of, d subshell can accommodate maximum of 10 electron. So this is the right answer. I think it's clear. Moving on to next question. So moving on to question number 21. Which of the following is not permissible arrangement of an electron in an atom? Right. So here option 1, n is equal to 5. Now what is the equation to calculate L value? L is equal to 0 to n minus 1. Now, what is the equation to calculate 0 to n minus 1? And what is the equation to calculate ML value? ML value is equal to minus L to plus L. So here n is equal to 5. So n is equal to 5 means L can have value 0 to n minus 1. That is 0, 1, 2, 3, and 4. Right. 0 to n minus 5. N minus 5 means 5 minus 1. That is n minus 1. That is 5 minus 1, 4. So L can have values 0, 1, 2, 3, 4. N value is 5. 5 minus 1. 0 to 5 minus 1. 5 minus 1 is equal to 4. Now here L value is given 3. So I'm taking only L value 3. L value 3 means ML can have value minus 3, minus 2. ML is calculated using this equation, minus L2 plus L, that is minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3, right? Now here M value is equal to 0. So N is equal to 5, L can have value 0, 1, 2, 3, 4. Here we have taken 3, L is equal to 3. If L is equal to 3, ML can have value minus 3, minus 2, minus 1, 0, 1, 2, 3. And here ML is given as 0. So this is right. If n is equal to 5, L can have value 3 and M can have value 0, and S can have plus or minus out. This one is correct. We have to find the arrangement which is not permissible. So this one is correct. Now second one, n is equal to 3. So L can have value 0 to 3 minus 1, that is 0, 1, 2. Now here n3, L2. L2 is taken. So N3, L2 is taken. Now L2 means ML can have value minus 2, minus 1, 0, 1, 2, right? ML minus 3. That is not possible. Here L is taken as 2. If L is equal to 2, ML can have value minus 2 to plus 2. Minus 3 is not possible. So this is the wrong arrangement. So answer option 2. Wrong arrangement, answer option 2. Moving to next question. A PN photodiode is made up of a material with a band gap of 2.0 electron volt. The minimum frequency of the radiation that can be absorbed by the material is nearly. Okay. So here a diode, we have a PN photodiode is there, and it is having a band gap of 2.0 electron volt. This is the band gap of the diode. Now you know that for a diode, if you consider PN diode or a NP, any diodes, there is band gap. Okay, this is the band gap, or you can call this as energy gap. So actually this is the energy. 2.0 is the energy of this energy gap. Okay, the band gap is 2.0 electron volt. So for a PN photodiode, it is made up of a material, and material is having a band gap of 2.0 electron volt. That band gap is also known as energy gap. So this is the energy. Now, the minimum frequency of radiation that can be absorbed by the material is nearly. So we have to find frequency. What is the equation to calculate frequency? Frequency. If energy is given, frequency is calculated using this equation. E is equal to h nu. This is the relationship between frequency and energy. So you can calculate frequency if you know energy by using this equation. E is equal to h nu. So E is equal to h nu. So nu is equal to E by h. Now E by h. Now Now E is equal to nu is equal to E by h, right? E by h. Now E is 2 electron volt and h is 6.626 into 10 raised to minus 34 joule second. Here h is expressed, or unit of h is joules, and unit of energy is electron volt. That is not possible. If you are taking h in joules, you have to take energy in joules itself. But here energy is given in electron-volt. So you have to convert this electron volt to joules. Okay, you have to convert this electron volt to joules. Now you know that 1 electron volt is equal to 1.6 into 10 raised to minus 19 joules. 1 electron volt is equal to 1.6 into 10 raised to minus 19 joules. So 2 electron volt means 2 into 1.6 into 10 raised to minus 19 joules. So 2 electron means 1 electron volt is 1.6 into 10 raised to minus 19 joules. So 2 electron volts means 2 into 1.6 into 10 raised to minus 19 joules. So instead of 2 electron volt, you can write 2 into 1.6 into 10 raised to minus 19 joules. Joules and joules cancel each other. So frequency is equal to, now if you divide 2 into 1.6 into 10 raised to minus 19 divided by 6.626 into 10 raised to minus 34, you will get nearly 3.2 something, 3.2 into 10 raised to 14 hertz. And this value is nearly equal to or near to 5 into 10 raised to 14 hertz. This value is nearly equal to, or it is near to 5 into 10 raised to 14 hertz. So answer option 3. I think it's clear. Moving on to next question. If uncertainty in position and momentum are equal, then uncertainty in velocity is equal to. So according to Heisenberg uncertainty principle, delta x into delta p greater than or equal to h by 4 pi. Okay, we can consider it is equal to h by, greater than or equal to. So I'm removing greater than, let it be equal. So delta x into delta p h equal to h by 4 pi. This is uncertainty in position and this is uncertainty in momentum. If uncertainty in position and momentum are equal, then uncertainty in velocity. So here they have given that uncertainty in position and uncertainty in momentum are equal. According to Heisenberg uncertainty principle, delta x into delta p greater than or equal to h by 4 pi. And they have given that position and momentum are equal. Uncertainty in position and uncertainty in momentum are equal. So instead of delta x, you can put delta p itself. So delta p into delta p equal to h by 4 pi. That is delta p square is equal to h by 4 pi. Now, what is momentum? What is actually momentum? Momentum means Here given delta x is equal to delta p, uncertainty in position, moment, vehicle. Now what is p? Momentum. Momentum is equal to mass into velocity, right? So instead of p, I am writing mass into velocity. That is that m into delta v whole square. It is delta p square. So momentum means mass into velocity. So that is m into delta v whole square is equal to h by 4 pi. So this will become m square into delta v square equal to h by 4 pi. So delta v square is equal to h by 4 pi into m square. So v delta v is equal to, taking root, you will get root of h by 4 pi m square. We have to calculate uncertainty velocity, that is delta v. You have to calculate uncertainty velocity. So delta v is equal to root of h by 4 pi m square. H by 4 pi m square. Okay, so no values are there. H by 4 pi m square. Option A, option B, option 3, and option D. You cannot find this value. So again, I'm taking, okay, now we got like this, root of h by 4 pi m square. Now again, I'm going to short down this equation. So delta v is equal to root of 4, root 4 is equal to 2, right? So I'm taking 2 outside, so 1 by 2. Now root of m square is equal to m, h by pi, right? 1 by 2m, root of 4, 2, root of m square m. So 1 by 2m root of h by pi. 1 by 2m root of h by pi. Answer option 2. 1 by 2m root of h by pi. I think it's clear. Question number 23. Moving on to question number 24. The measurement of an electron position is associated with an uncertainty in momentum, which is equal to 1 into 10 raised to minus 18 grams per grams centimeter second inverse. The uncertainty in electron velocity is, so here uncertainty in momentum is given. The measurement of electron position is associated with an uncertainty in momentum, which is equal to, so uncertainty in momentum is given 1 into 10 raised to minus 8 grams centimeter second inverse, right? Here uncertainty in momentum is given. We have to calculate uncertainty in velocity. Now what is delta? What is p? What is momentum? Mass into velocity. So instead of p, I am writing m delta v equal to 1 into 10 raised to minus 18 grams centimeter second inverse. Now we have to calculate delta v. So delta v, uncertainty in velocity, we have to calculate the uncertainty in velocity. That is delta v is equal to 1 into 10 raised to minus 18 grams centimeter second inverse divided by m. Now here m value is given 9 into 10 raised to minus 18. So 1 into 10 raised to minus 18 divided by grams centimeter second inverse divided by mass value is given 9 into 10 raised to minus 28 grams. 9 into 10 raised to minus 28 grams. So grams and grams cancel each other. Now if you divide this 1 into 10 raised to minus 18 by 9 into 10 raised to minus 28, you will get approximately, you will get, I'm going to write the value, you will get 1.09 into 10 raised to 9. You'll get 1.09 10 raised to 9 centimeter second inverse. You will get 1.09 into 10 raised to 9 Siemens, centimeter second inverse. So answer is 1 into 10 raised to 9 centimeter second inverse. Answer option 2. I think it's clear. Moving on to next question, question number 25. Consider the following set of quantum numbers n, l, m, and s. Which of the following set of quantum number is not possible? So which of the following set of quantum number is not possible? Here 4 values are given. Which of the following is not possible? Now n is equal to 3. If n value is equal to 3, L can have value 0, 1, 2. Right? Now here L value is given 0. If L value is equal to 0, ML can have value 0. And S can have, right. Now S can have plus or minus 1. This one is right. Which of the following set of quantum numbers is not possible? This one is possible. Now B, this is option A. Sorry, this one is A and B. N is equal to 2 and L is equal to 2. That is not possible. If N is equal to 2, L can have value 0 and 1. 2 is not possible because equation to calculate L is 0 to N minus 1. Right. So if n is equal to 2, L can have value 0 and 1. This is not possible. L is equal to 2. That is not possible. So B is wrong. Now moving on to question C. N is equal to 4. So L can have value 0, 1, 2, 3. 3 is there. 4, 3. Now, and if L is given 3. So if L is equal to 3, ML can have value minus 3, minus 2, minus 1, 0, 1, 2, 3. So ML is equal to 3. L is equal to 3. If L is equal to 3, here given L is equal to 3, ML can have value minus 3, minus 2, minus 1, 0, 1, 2, 3. That is possible. Minus 2 is possible. So this one is possible. And S can have minus half or plus half. So this one is correct. Now D. N is equal to 1. So L can have value only 0. And ML can have value only 0. But here it is given minus 1. So this one is wrong. Now, option E. E. N is equal to 3. So L can have value 0, 1, 2. Right? N3 means L can have value 0, 1, 2. 0 to N minus 1. 0 to N, 3 minus 1, 2. Now, ML can have value. So if L is equal to 2, here given that L is equal to 2. So if L is equal to 2, ML can have value minus 2, minus 1, 0, 1, 2. 3 is not possible. So this one is also wrong. So B, D and E are wrong. B, D and E are wrong. B, D and E are wrong. B, D and E. Option 4. Answer option 4, right answer. B, D and E are wrong. 1 minute. Here B, D and E are wrong. Option 4. B, D and E. B, D and E are wrong. I think it's clear. Moving on to question number 26. With which of the following configuration an atom has the lowest ionization enthalpy? Lowest ionization enthalpy. So here, if you consider this configuration, 1s2, 2s2, 2, this is a completely filled. Here 2p is completely filled. Completely filled. So completely filled have always high energy. High ionization energy. For completely filled orbital, ionization energy value are usually high. So high ionization value because it is completely filled orbital. Completely filled orbital. Now here this is not completely filled, but actually we know that 1s2, 2s2. This is configuration of neon. And this is configuration of fluorine. We know that fluorine is having high ionization energy. Now this is the configuration of 1s2, 2s2. Now this is half filled. Here P is half filled. Half filled always have high ionization. Half filled and completely filled are always having high ionization energy. So high ionization energy. This is the configuration of nitrogen. Now here 1s2, 2s2, 2p5, 3s1. 2p5, 3s1. Okay, one electron is promoted to 3s orbital. Now here 1s2, 2s2. I think it may be 2p6. I don't know. I think it may be wrong. It is maybe 2p6. 1s2, 2s2, 2p6, 3s1. Actually this is 2p6. Okay, 1s2, 2s2, 2p6, 3s1. Okay, it is not 2p5. It is 2p6. 2p6, 3s1. Now this is the configuration of sodium atom. Sodium belongs to S block. S block elements are having always lowest ionization energy. Along a period, ionization energy increases. Sodium belongs to first group. They always have low ionization energy. So lowest ionization energy is for option 4. Actually, this is not 2p5. This is actually 2p6. So configuration of sodium. Sodium belongs to first group. First group element. Along a period, ionization energy increases. That means first group is having lowest ionization energy as possible. So answer is option 4. These two are half filled and completely filled. They are having higher ionization energy. And this is the configuration of fluorine. Fluorine is having small size. For small size, along a period, size decreases, ionization energy increases. I think it's clear. Moving on to question number 27. The mass of an electron 9.11 into 10 raised to minus 31 kg. Planck constant is 6.626 into 10 raised to minus 34 joules second. The uncertainty involved in the measurement of velocity within a distance of 0.1 angstrom is. So we have to calculate uncertainty in velocity, right? Uncertainty in velocity. The mass of an electron is given as 9.11 into 10 raised to minus 31 kg. Planck constant 6.626 into 10 raised to minus 34 joules second. The uncertainty involved in the measurement of velocity with the distance of. Okay, so equation according to Heisenberg uncertainty equation, delta x into delta p greater than or equal to h by 4 pi. Now we can take it as equal again. Now what is delta p? Delta p is equal to m into delta v. So delta x into m into delta v is equal to h by 4 pi. Right. Now we have to calculate delta v. So m delta v is equal to h by 4 pi delta x. Now I'm taking this m to this side. So you'll get delta v is equal to h by 4 pi delta x into m. So here delta x, we have to delta v. We have to calculate measurement of velocity, right? Uncertainty involved in the measurement of velocity. We have to calculate delta v. So delta v is equal to taking all the terms to right side. You will get delta v is equal to h by 4 pi delta x into m. So delta v is equal to h value 6.626 into 10 raised to minus 34 divided by 4 pi 3.14 into delta x 0.1. Here it is given that distance is 0.1 Armstrong, which is equal to 0.1 into 10 raised to minus 10 meter. We know that delta x is given as 0.1 Armstrong. So converting Armstrong to meter, you will get 0.1 into 10 raised to minus 10 meter. 1 Armstrong is equal to 10 raised to minus 10 meter. So 0.1 Armstrong is equal to 0.1 into 10 raised to minus 10 meter into mass 9.1 into 10 raised to minus 31 kg. Now after doing this, you will get delta x is equal to 5.799 into 10 raised to 6 meter per second. After division, you will get 5.799 into 10 raised to 6 meter per second. Answer option A, 5.79 into 10 raised to 6 meter per second. Okay, I think it's clear. This is the uncertainty in velocity. Uncertainty in velocity. Delta 5.799 into 10 raised to 6 meter per second. I think it's clear. Moving on to question number 28. The orientation of atomic orbital is governed by orientation of atom. Which quantum number gives the orientation of atomic orbital? Now, principal quantum number gives the shell in which electron is present, the average distance of the electron from the nucleus. It gives the energy of the orbital, energy of the electron. It gives the angular momentum of an electron in an orbit angular momentum. We have discussed this when we took theory. When we discussed theory in theory classes, we have discussed this one. Now, azimuthal quantum number gives the subshell in which electron is present. It gives the energy of the subshell. It gives the shape of the orbital. It gives the orbital angular momentum. MVR is equal to root of L into L plus 1 into H by 2 pi. Now, magnetic quantum number, it gives the orbital in which electron is present in a subshell. It gives the orientation of electron. It tells about the splitting of spectra in the presence of magnetic field. So magnetic quantum number gives the orientation of electron. So here, the orientation of atomic orbital. Atomic orbital is filled with electron. So orientation of electron is given by magnetic quantum number. Atomic orbital is filled with electron. So orientation of atomic orbital or electron is given by magnetic quantum number. So answer is magnetic quantum number. Now what does spin quantum number give? Spin quantum number gives the spin of the electron. Spin quantum number gives the spin orientation of an electron. It gives the spin orientation of an electron and it gives the spin angular momentum, that is root of S into S plus 1 into H by 2 pi. Spin angular momentum. So you have to study the uses of or application of these quantum numbers. Okay, you have to study the applications or uses of these quantum number. I think it's clear. So orientation of atomic orbital or orientation of electron. Atomic orbital is filled with electron. So orientation of electron is given by magnetic quantum number. Moving on to next topic. Moving on to next question. Question number 29. The energy of second Bohr orbital of hydrogen atom is 328 kilojoules per mole. Hence, the energy of fourth Bohr orbit would be. Now, we have to calculate energy of an electron in the fourth orbit. The energy of second Bohr orbit of hydrogen atom is 328 kilojoules per mole, and hence the energy of fourth orbit. We have to calculate fourth orbit, energy of fourth orbit. First orbit, second orbit, third orbit, fourth orbit. We have to calculate energy of fourth orbit. Here, energy of second orbit. Let's give one. Now, we know the equations to calculate energy. We have learned this much equation to calculate energy of orbit. En is equal to minus 2.18 into 10 raised to minus 18 Z square by n square joules per atom if energy is expressed in joules per atom. Now, if you are going to express in ergs per atom, then equation is minus 2.18 minus 21.8 into 10 raised to minus 12 into Z square by n square. Ergs per atom minus 21 point, or you can take it as minus 2.18 into 10 raised to minus, if you take a point to this side, you will get 10 raised to 11. You can take 10 raised to 11 also. Minus 2.18 into 10 raised to minus 11. You can take this also. Instead of 21, you can take 2.18 into, okay, instead of, so if you took a point to this side, you will get 10 raised to minus 11. Okay. Into Z square by n square x square. Now in electron volt, energy is minus 13.6 Z square by n square electron volt per atom. Now in kilocalories per moles, energy is minus 313.6 Z square by n square. Now in kilojoules per mole, energy is minus 1312 Z square by n square. So these are the equations to calculate energy of each orbit in different units. These are the equation to calculate energy of orbits in different units. Now here answer is given in kilojoules per mole. That means you have to choose this equation. You have to choose this equation. Here answer is given in kilojoules per mole. So you have to choose this equation. Z square by kilojoules per mole. Actually this is per mole. Okay, kilojoules per mole. Okay, kilojoules per mole. So you have to choose this equation. This is the apt equation to calculate. So by using this equation, I'm going to calculate the value. So fourth orbit. So equation is En is equal to, what is the equation? En is equal to minus 1312 Z square by n square kilojoules. So minus 1312 Z square by n square kilojoules per mole. Right. Now energy of fourth orbit. So fourth orbit means E4. E4 is equal to minus 1312 into hydrogen atom. We are going to calculate energy of fourth orbit of hydrogen atom. For hydrogen atom, Z value. For hydrogen atom, Z value is equal to 1. Atomic number of hydrogen atom is 1. So 1 square by, here N is 4. 4 square kilojoules per mole. Right. So E4 is equal to minus 1312 into 1 square divided by 4 square, 16 kilojoules per mole. After dividing, you will get energy is equal to minus 82 kilojoules per mole. So this is the energy of fourth orbit. This is the energy of fourth orbit in hydrogen atom. Minus 82 kilojoules per mole. Okay. So you have to choose the equation of energy based on the answer. Sometimes answer is given in kilojoules per mole. Sometimes it may be given in joules per atom, or sometimes it may be given in ergs per atom. So based on the answer, you have to choose equation of energy. Based on the answer, you have to choose equation of energy. I think it's clear. Based on the answer, you have to choose the equation of energy. Here, energy is given in kilojoules per mole. So we choose this equation. Okay. So it's clear. I think it's clear.